This video is a continuation of the previous lecture. In the previous video, we were talking about mechanical energy of a macroscopic object, which is equal to Ke plus Pe. In the previous video, we discussed the kinetic energy. Now our concern is the potential energy. Potential energy. The definition of a potential energy is the energy processed by a body by virtue of its position relative to others or stresses. So the potential energy is the energy processed by a body by a virtue of its position relative to others, stresses within itself, electric charge, and other. But since we are talking about mechanical energy, then the electric charge is excluded for now. Now let us get deep in the potential energy. Potential energy is decomposed into two types of energy. First, GPE, which is the gravitational potential energy, and EPE, the elastic potential energy. Let's start with GPE, which is equal to mass of the object, which is measured in kilograms, multiplied by the gravity, which is newtons per kilogram, multiplied by h, measured in meter. So then the GPE, which is the gravitational potential energy, is equal to mass times g times h, where mass in kilogram, gravity in newtons per kilogram, and h is in meter. Now, if we let this be our reference level for gravitational potential energy, then every point or every object is at the distance h from this level, then this object S has a gravitational potential energy greater than 0. So the more h, or as the elevation increases above the GPE level, then the stored energy increases as a GPE. Now, if we have an object below the GPE level, then this object S also possesses a GPE, but in negative. GPE is less than 0. So GPE is a potential energy depending on the position, as we've said before. Then the gravitational potential energy depends on the elevation away from the GPE level. Now let's speak about the elastic potential energy. As we have said, also potential energy depends on the stresses with the body itself. So if we have a spring of stiffness K, then if we elongate or compress this spring, then we are making stress on the spring. So the elongation and the compression gives the spring an energy called EPE, which is equal to half kx squared, where k is the spring stiffness. So the more we compress, or the more we elongate the spring, then the energy, of course, under the tolerance of the spring stiffness, which is K. So the more we compress, or the more we we elongate the spring, then the energy is stored as an elastic potential energy. Now, let's speak about the force of EPE first. Now let's speak about the force F, which is the tensional force of the spring. Then F is equal to minus KXI. The negative sign is here because the force tension of the spring is always against the deformation. So if the spring, let this spring L0, then if we are tending to elongate, so if we are tending to elongate the spring L by X, then the force will be acting against the deformation. And also if this spring of length L0 is going to be compressed, then the force of tension will be also opposing the deformation, which is compression. So the negative sign of F in the tension, in the force tension of the spring, is always opposing the deformation. Now let us see how this expression, where does it come from? So as we said that F is equal to, and this is the tension, is equal to minus Kx. Now if we have dW, which is the infinite small amount of work done by this force, it will be equal to minus Kx dx. But as we also know that work is equal to the scalar product multiplied by the displacement, which is equal to F d cosine alpha. But here alpha is equal to 180 because the angle between the force F and the displacement X is 180 degrees. So because the angle between the displacement F and the, so the angle between the force tension and the displacement X is 180 degrees. So therefore dW is equal to Kx dx. So if we make the integral both sides, we get W is equal to Kx power 2 over 2 x initial x final. So therefore W, which is equal to the energy EPE stored in the spring, is equal to half Kx square, which is measured in joules. So let us make a quick revision about what we have just said now. This is the potential energy. This is the potential energy. It is decomposed into GPE and EPE. GPE is equal to mass times G times H. As much as we are away, or as much as H increases, then the stored energy GPE increases. Now for EPE, which is a physical quantity, is equal to half Kx squared. We start with its force, which is equal to minus Kxi. We said before that the minus sign, the negative sign here, is because that the tensional force is always against the displacement, or it's against the deformation of the spring. So if you are tending to elongate the spring, then the force tension will be to the left, and if you are compressing the spring, so then the tensional force will be to the right. Now if we take a dW, which is an infinite small quantity of work, it will be equal to minus kx dx. But as we know that work is a scalar quantity, that f dot d equal f d cosine alpha. But here alpha is 180 degrees because the force tension, because the angle between the direction of the force and the displacement x is 180 degrees, and cosine 180 degrees is equal to minus 1. So minus and minus we get plus, and we make the whole integral for dw, we end up with w and kx squared from 0 to final. So then W, which is the elastic potential energy stored in the spring, is equal to half k x squared. Also remember that physics is fun, so please like, share and subscribe.